Hello everyone, welcome to my presentation on molybdenum disulfide membrane-based ultrasensitive temperature sensor. To start with, I will talk in brief about NEMS resonators and its application. It has various applications like mass sensing, charge and force detection, single spin detection. The basic principle of working is simple. We detect the change in frequency shift of the resonator when exposed to an external stimuli. Two-dimensional materials are ideal for NEMS-based sensing application because of its ultra-low mass and high vibrational frequency. It is extremely sensitive to external stimuli, strain in the membrane. These devices can be fabricated at large scale using CVD-based 2D materials, and they also possess large frequency tunability. In this work, we fabricate MOS2-based drum resonator on insulating sapphire substrate with local backgate configuration. The fabrication process involves patterning of backgate with E-beam lithography. Over this, silicon dioxide is deposited using plasma-enhanced chemical vapor deposition, which acts as a dielectric. Then we etch SiO2 to form the circular cavity using reactive ion etching. Thereafter, source-drain contact are deposited using E-beam lithography. At the end, MOS2 flake is exfoliated on a PDMS stamp and is transferred over the cavity to get the suspended MOS2 membrane resonator. This is the scanning electron micrograph of the suspended MOS2 membrane over a 2 micrometer cavity with 300 nanometer depth. The devices are actuated using capacitive technique and detected using homodyne detection scheme. The simplified measurement schematic is shown to the right. The resonant response of the device showing two prominent vibrational modes is shown in the figure below. The resonant frequency of the membrane can be tuned by changing the strain in the membrane through backgate bias. Here we show resonant frequency tuning of the fundamental mode with temperature. The resonant frequency decreases with increasing temperature. Increasing temperature leads to thermal expansion of the membrane, leading to decrease in intrinsic strain and resonant frequency of the membrane. The thermal coefficient of frequency of our fabricated device is -283 ppm per Kelvin, and the table here shows some of the previously reported TCF values for NEMS resonators. The higher TCF value for our device means it has better temperature sensitivity in comparison to MEMS devices. Then we also measure the frequency stability of our device at room temperature by calculating the Allan deviation. This is essential to estimate the magnitude of frequency fluctuation and thus determine the ultimate temperature sensitivity of MOS2 resonator. The estimated temperature sensitivity, assuming linear frequency temperature characteristics, is in the sub-Kelvin limit. So in conclusion, we fabricated MOS2 drum resonator and characterized its mechanical response using homodyne capacitive scheme. We observe a decrease in resonant frequency with increasing temperature. We estimate the frequency stability and temperature sensitivity of our resonator. Further, it should be possible to improve the sensitivity by improving the transduction scheme. I would like to thank you everyone present and the organizing members of the IEEE Sensors Conference.